Welcome in, guys. It's Mr. Haack, and today's video is going to be on 3.4 and on our derivative worksheet, or mini lab, whatever you want to call it. Investigation, same thing. So let's start with 3.4, number 8. And for number 8, we have g of t equals t plus 1, t squared minus t plus 1. Now, before I dive into doing the problem, I want to make sure that you guys are clear on the difference between some things. So we have derivative rules, and we have two families of rules. We have what I call the arithmetic rules, and these can have the other rules within them, and then we have the function rules. And you should start to be making that kind of clear in your head right now. Of the arithmetic rules, we have the sum and difference rule for derivatives. We have the product rule, we have the quotient rule, and we have what will come later, which you haven't learned yet, the chain rule. And this is going to be the hardest one. And then for the function rules, that's like, what's the derivative of x squared? Well, we use the power rule for that. What's the derivative of natural log of x? What's the derivative of e to the x? What's the derivative of cosine of theta? Stuff like that. What's the derivative of arc cosine of x, right? Of a ratio, and so on. So these will have their own algorithms. Each of these will have algorithms. And what we're starting with now is we're looking at two functions that fall into the power rule family. All of these fall into power rule. Every one of the, like the individual derivative for this, the individual derivative for this, individual derivative here, here, and here are all power rules. But they're in parentheses, which means this guy right here is some function f, and this guy here is some function g. I could use whatever letters I want, and they're being multiplied by each other. So how does the fact that they're being multiplied by each other impact the derivative? And that's going to be the product rule, because a product is a special rule we're going to use for the derivative of products. And if we swing over to the cloud, you'll see that I have the product rule written out right here. And I'm going to go ahead and just write that too. I'm going to use u instead of w. I'm going to say if u equals the product of two functions f and g, then u prime, or w prime, whatever, you can use w if you want, will equal the first one times the derivative of the second one, plus the second one times the derivative of the first one. Okay, and again, there are some really intuitive ways to understand why this rule is what it is and why it makes sense. But our goal for the summer is not to get too much into theory, and to just teach you the basics. So I'm now going to so add this to your derivative rules sheet, right? This is summer. We got a fast pace. You need to add this. You should have a big page of all your derivative rules. Write down product rule. Okay. You need to memorize the product rule. You do need to have this pattern memorized, otherwise you're going to be in between a rock and a hard place. It'll be very hard to do the calculus if you don't. And I also just want to make sure that you guys see that in the calculus cheat sheets folder, if you go into cheat sheets, you'll see that all the derivative rules are nicely typed out and formatted on a sheet that I have here. So plenty of these are online, and you can use this one here, and you'll see here's the power rule, the exponential rule, and then they always seem to put the arithmetic rules together with the function rules, which I think is odd. I think they should keep these separate, but you can see that the product rule, this is just a different way of writing it, and they're writing it here. So let's go ahead and dive into these now. And we'll talk a little bit about the dx notation as we go. We're not going to get too worried about that right now. So for this function here, well, I guess we'll talk a little bit about it right now. So this would be d dt, because the independent variable is dt. So whatever your independent variable is, and this means the derivative with respect to time. So, and there's a parenthesis here. Okay, so you would put d dt of g of t here. So this is actually, you can either write it over here to the right of the fraction, okay? It's kind of like this times that, or you can write it like this, dg dt. Either way works, okay? So d dt of g of t, or dg dt, are the two ways that you would say that. And these are the same thing, okay? They're just different conventions of writing it out. So let's dive into how we actually do this problem now. So just look at the algorithm. First one times the derivative of the second plus second one times the derivative of the first. And you want to pause the video, say that back to yourself, and I would make that a little saying that you can do. Product rule. First one times the derivative of the second, second one times the derivative of the first. And that's it. So first one times the derivative of the second one. Derivative of the second one is going to be sum and difference rule for the internals and power rule. So 2t minus 1 plus 0, I won't write that part. And now plus the second one times the derivative of the first one. And derivative of t will be 1, derivative of 1 will be 0. So we're going to have 1. Now we simplify. First of all, you're done here. You don't really need to simplify, but if you want, you can. So we'll go ahead and do that. So 2t squared minus t plus 2t minus 1. Then we'll do this side separately. Well, this is just it is what it is because it's times 1, so that makes that easy. Now we have 2t squared plus t squared, which will give us 3t squared. We have negative t plus 2t and another negative t, so 2 negative t's plus 2 positive t's will be 0 t's left over, and negative 1 plus 1 will be 0. So I'm getting a final answer for dg dt of 3t squared. So as we do these videos, make sure to pause and try to work ahead and stay one step ahead of me, that kind of thing. And then see if you get the same thing that I get. So you would like pause up here, try to do this problem on your own, or as soon as I get to here, or as soon as you see me starting, try to pause it and see if you can anticipate and get ahead. That's the best way to use these videos. Okay, now that's using the product rule, but note that the instructions said that you could also just expand this first, part B. They required you to do that. So the other way to do that is to go like this. So we take t plus 1, and instead of doing the product rule with it in its current form, we're going to expand this forward. So this is t plus 1 times t squared times negative t and times 1. So I'm going to do that. So t squared times t plus 1 minus t times t plus 1 plus 1 times t plus 1. So I'm going to distribute that t plus 1 to each term in the expression that it's being multiplied by. And we're going to get t cubed plus, yes, we're going to get t cubed plus t squared minus t squared minus t plus 1. Let me pause there. I feel like I made a mistake somewhere in just a second. No, that looks correct. Okay, so now we have t squared minus t squared, so that falls out. We have negative t plus t, so that falls out. So we're left with t cubed plus 1, and all of that is equal to g of t. And now we're ready. This is still g of t. Now we're ready to differentiate. So we can do dg dt, which is the same as g prime of t. These are just different notations. These mean the same thing as well, so I'm just writing both to get you familiar with the notation. Okay, and g prime of t would be do the power rule on this and do the power rule on this. So the power rule of t cubed is 3t squared, and the power rule of 1x to the 0th, okay, is that, well, I guess you shouldn't call it a power rule. This is a constant rule, and that will just be 0. Yeah, so it's not technically a power rule for that one, sorry. Okay, so that looks good, and that's our answer, and we get 3t squared this way as well. So now let's take a look at number 10. You're hunting and pecking. I'll stall for a little bit and leave that up as I write it out. Okay, and we got this guy, and they want us to use the product rule first, and then they want us to expand it out and do it that way. So we'll do the product rule first. So first one, so we're immediately going to write h prime of z. We could do dh dt, excuse me, dh dz. The independent variable is what goes down here. It's a z, so z here. The output variable goes here. I could write it this way, I could write it this way. I can also do this. d dz of h of z. Okay, so you can write it all these different ways. I kind of wrote all of these sloppy, so let me write them all nice. D dz of h of z is one way to write it. Dh dz is another way to write it. And h prime of z is another way to write it. These are all just rivaling notations. Okay, you just pick the one that you're comfortable with. These are rivaling notations. If you'd like to know, this one here is called, it is kind of similar actually. I've read the original Leibniz. It's called Leibniz Notation. Okay, that one's called Leibniz Notation, so is that one. They're just different standards of Leibniz Notation. This one here, okay, these guys are called prime notation. Okay. All right, so let's go ahead and take a look at what we would get here. So it's going to be the first one. Just rewrite it, times the derivative of the second one, which is 1, plus the second one, times the derivative of the first one, which will be 3z squared. And let's see what else. So it'll be 8z to the first, and then plus 1. Now we expand this all out, so this is easy. This one is just going to drop down as z cubed plus 4z squared plus z. And now this one will be a z minus 1 times each of these terms. So plus 3z squared times z minus 1 plus 8z times z minus 1. And I'll have to drop the other one down here, plus z minus 1 times 1. It's getting distributed to each of those terms. All right, so now we're just going to drop everything down again. So z cubed plus 4z squared plus z, we'll go ahead and expand over here, plus 3z cubed minus 3z squared. That takes care of that one, plus 8z squared minus 8z plus z minus 1. And once we get all of that written out, let's just combine like terms. So we got z cubed and z cubed. So we're going to have 4z cubed. And then here we're going to have 4z squared minus 3z squared. So that's going to be 1z squared left over. Plus 8z squared will be 9z squared. Okay. Now I have a z here and a minus 8z here and a z here. So it's 2z minus 8z, which would be minus 6z's. I crossed them out to make sure I got into all of them. And then here minus 1. And that looks good. That is the correct answer. Now, I'm not going to do the second part on this one. Not doing second part. Because you know what to do and you know what the answer is. So what you want to do on the second part is you're going to multiply this times z and that times 1. You're going to distribute this whole thing to the z and distribute that whole thing to the 1. And you're going to do the opposite of factoring, which is called expansion or expanding. And you're going to expand this, okay, all the way out, simplify, and then do the power rule. And you know that it should match this answer. So that's a great little thing to practice on your own. I did the first one to show you a sense of what it's like. But the thing that you don't know how to do is the part that I just did, which is the product rule. First one times the derivative of the second, plus second one times the derivative of the first. So hopefully that helps, and we're going to go ahead and move on to the next one, number 40. All right, so number 40 is y equals 4 over p cubed. And we can do this two different ways. We can use quotient rule here with power rule, or we can just use power rule. Typically only power rule would be the best because the 4 is technically a constant. So I'll just remind you that this is 4p to the negative 3. And so if we want to do the power rule, so y prime would equal negative 3 times 4. We move this to the front and multiply it. Then, and that's a dot, and then we subtract 1 from the power, and we get negative 12 p to the negative 4. and then write it like a normal person in standard notation. And we're going to get negative 12 over p to the fourth. Okay, so we know what we should get if we do the quotient rule, which we're going to do next. So the quotient rule, let's go ahead and write down what that rule is and look at our cloud folder. So the quotient rule, and I'll step you through what all of this is. Denominator, write this out, pause the video, and then follow along. Okay, so this is the quotient. This part right here, f of x over g of x, you're taking a derivative, d dx, of some quotient, some two functions, one divided by the other, f and g. And in this particular case, our f and g would be 4, okay, and p cubed. Function 4 is a function. It's a small function. It's a simple function, but it's still a function. So this is function 4 divided by function p cubed. And so that would be the f and the g in this case. And what this is telling you the algorithm is denominator times the derivative of the numerator minus numerator times the derivative of the denominator over the denominator squared. And you want to pause the video, write that out, and be able to say that. I'm going to say it one more time. Denominator times derivative of the numerator minus numerator times the derivative of the denominator over the denominator squared. And when you can say that out loud, then you'll essentially have it memorized and you'll be good to go. So this is much harder to do in this case. I would say this is ideal. Okay, if you have a constant, just treat it as a power rule, and you'll see why. But you can certainly do the quotient rule here, and it's good practice. So denominator, okay, so p cubed times the derivative of the numerator, and the derivative of the numerator is 0. And this is why this is lengthier, because that will obviously fall out because the derivative of a constant is just 0. But it still works, as we'll see. So denominator times derivative of the numerator minus numerator. Okay, and put parentheses here, always. Super important. I'm just going to put eyes on it, okay? On these guys. Always have parentheses. It's so important. All right, so denominator times derivative of the numerator minus numerator times derivative of the denominator. 3p squared, okay, is the derivative of p cubed, over denominator squared. Okay, and now we're going to simplify this guy out. We're going to have 0 minus 4 times 3 is 12, so we're going to have negative 12p squared up here. And down here, we have a power of a power, so make sure your exponential rules are good. And of course, we're going to multiply those, giving us p to the 6th. And then when we cancel out here, we're going to get 2 here, 6 here, so there'll be 4 left down here, and none left up here. And so we're going to get negative 12 over p to the 4th. So you can see that we get the same thing either way. And they didn't tell you which method to do here. So you might have done many of you I know historically will do the quotient rule here. But bear in mind, this one might be a little easier to just merely do the power rule, because you can treat the 4 as a constant and this is a negative power. And therefore the power rule would be sufficient. There's more than one way to skin a cat. We're all going to do some of these derivatives subtly different than other folks in the class, and that's perfectly fine. Do whatever method is comfortable for you. There are wrong methods, though. Don't do those. And you'll know that because you won't get the same answer, or you'll violate some algorithm or rule in your algebra. And that can happen too. But as long as you're doing valid rules, you have the liberty to pick the one that's more convenient for you. All right, let's take a look at the next problem, which will be 46. And for 46, we see that we have x minus the difference of x and 1 times the difference of 2x squared and 1, and that product divided by x cubed minus 1. So 46, and we have h of x equals x minus 1, 2x squared minus 1, all over x cubed minus 1. So deep breaths will be just fine. So h prime of x is going to be the quotient rule. And again, this whole thing up here is your f, and this whole thing down here is your g. But look that f is actually a product. Okay, so we're going to have a product rule within a quotient rule. So the biggest rule we're doing is the quotient rule. But then inside of this quotient rule we're about to do, we're going to have a product rule in there. And we know that because we have a product up here. So we're going to find it, we're going to see it real soon. So denominator, so say the rule with me real quick. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So denominator times the derivative of the numerator. Okay, so I'm going to write d dx of x minus 1 times 2x squared minus 1. Before I solve it, I'm just going to write it out. That's where we're going to use the product rule. Okay, so inside of our quotient rule, we have to do a miniature product rule right there. So before I solve it, I'm going to write it out in Leibniz notation just to keep my work structured, and then I'll solve it on scratch paper and then put the answer back in here. Then minus numerator, okay, put some nice big parentheses here. Don't forget your parentheses. I'm going to put i's again. Very important. Okay, so denominator times derivative of numerator minus numerator times derivative of denominator. This one's a little easier, but I'm still just going to put ddx rather. I don't know why I said two d's there. And x cubed minus 1, because I want to get everything set up, and then I'll use scratch paper and just fill in all the right parts. All over denominator squared. So that's what I get. So now I'm going to drop down my x cubed minus 1. And now I need to figure out what it's going to get multiplied by. Well, it's going to get multiplied by this guy, which I'm going to do up here in scratch paper. So scratch paper for the derivative of the numerator. And the derivative of the numerator is going to be x minus 1, first one times derivative of the second one. Okay, so second one's derivative will be 4x minus 0. So just 4x plus second one, 2x squared minus 1, times derivative of the first one. And negative 1's derivative will be 0, and x's derivative will be 1, so that's just 1. I'm going to distribute this here and here and add it to this one times 1 will just be itself, so that one just drops down, 2x squared minus 1. And now let me just distribute this, so we get 4x squared, we get minus 4x. Let's simplify if we can, which we can. 4x squared plus 2x squared is 6x squared minus 4x minus 1. So in my scratch paper I did this part. I now know that the derivative to the numerator is this. I'm now going to drop that down here for 6x squared minus 4x minus 1. And I'm going to do the same thing down here. I'm going to take this guy, and up in my scratch paper, I'm going to do the derivative of x cubed minus 1. This one's a little easier. It's just going to be 3x squared. Take 1 off the power, multiply the power in front, and take 1 and deprecate the power by 1. Derivative of minus 1 is 0, and so 3x squared is our entire derivative here. So we're good to go. I'm going to drop this part down. So big parentheses around everything. And then we're going to have parentheses around the x minus 1, 2x squared minus 1. The reason I maybe get a little overkilled here with parentheses is I don't want to lose any negatives. And you're subtracting this whole expression here. And then times 3x squared. So 3x squared. And I think that's the correct amount of parentheses. And then down here, we'll just drop down our x cubed minus 1 squared. By the way, don't expand this unless you need to. Unless it needs to, or it simplifies, or kind of check at end. But don't do it at the beginning right away. It's unnecessary. Okay, so the next thing we're going to do is we have to multiply this x cubed minus 1 by every term here in the expression giving us. I'm going to start way over here. Nice big equal sign. We're going to get 6x squared times x cubed minus 1. And by the way, you could have expanded this first and then done the quotient rule. Okay, that also works. Do you want more work at the start? Do you want more work at the end? It's 6 half dozen, one the other. So if you want to expand that first, if you took that approach and then did the quotient rule, that's perfectly fine, but you don't have to. So x cubed minus 1 times 6x squared, and then we're going to have minus 4x times x cubed minus 1. Then we're going to have minus 1 times x cubed minus 1. And then we're going to have, let's first simplify this above it. So 3x, so first we have to expand these. So that's going to give us 2x cubed minus x minus 2x squared plus 1. And then we're going to take all of that and multiply it by 3x squared. And then we're still subtracting all of those. So I'm still just going to leave my parentheses here, and we're just going to drop everything in. So that's going to give us 6x to the 5th minus 3x cubed, distributing this to each one, minus 6x to the 4th plus 3x squared. And we're subtracting every one of those all over x cubed minus 1 quantity squared. All right, now let's do another line here. Now we have 6x to the 5th minus 6x squared, distributed and distributed, minus 4x to the 4th plus 4x minus x cubed plus 1. Now we distribute the negative 1, or subtract each of the terms, however you want to think of it, minus 6x to the 5th plus 3x cubed plus 6x to the 4th minus 3x squared, all over x cubed minus 1 quantity squared. And now we combine like terms. So 6x to the 5th minus 6x to the 5th, those add out. Let's look at our 4th power now. So, and put a new fraction, and we'll just drop everything down. Okay, so we have negative 6x squared, and we have negative 3x squared. So I don't know why I did squared next, sorry. So that's going to be negative 9x squared. We'll just put that over here somewhere. Guess where it goes. Okay, let's do the 4th power like I said originally. Negative 4x to the 4th, positive 6x to the 4th. That's going to be 2x to the 4th left over. I'll rearrange them in descending order. Actually, I can squeeze it in there. Negative x to the 3rd, positive 3x to the 3rd will be 2x to the 3rd. I can't really squeeze it in there. I'll just put them out of order this time. So positive 2x cubed, and then I'll arrange them in descending order of degree at the end. And then we have plus 4x, and then plus 1. So let's go ahead and put them in descending order of degree at this time. And don't forget that this is h prime of x. So we'll drop down our h prime of x here, h prime of x as we go. And now we'll just pretty things up and see if there's any simplifying we can do. So 2x to the 4th plus 2x cubed minus 9x squared plus 4x plus 1 all over the difference of x cubed and 1 squared. And that should be correct. If we made any mistakes, I'll try to track them down now. You pause the video, see if you think I made any mistakes, and see if you can catch them. And we'll see here in just a second. Okay, and what I did is you can see that this answer is true. So I went ahead and typed in this whole giant expression that we got. I set it equal to the book's answer, and you can see that it comes out as true. So taking us back here, this would be the answer if you did it that way. And there's nothing wrong with doing this, okay? This is correct. This is not in simplest form, okay? It's not in simplest form, but that's okay. There's no requirement that you do things in simplest form. And as long as you follow the rules, which we did, and just here, look back at them, you're going to be good to go. So just write out that pattern, and you don't need to simplify anything. And this thing would be just fine to use. It's not too hard to calculate things in there. So that's one way to do it. Another way to do 46, however, let's go ahead and write it out one more time, is to simplify first. So some of you may have noticed that we have something in here that will simplify, and you might have noticed that. Oh, and it looks like when I first wrote it, I forgot to write the, oh no, that's not the derivative, yeah. Some of you might have noticed that we have a difference of 2 cubes in the original expression. So here's the original expression. And some of you might have snapped to the fact that, wait a second, that's one of those special cases from Algebra 2 of a difference of 2 cubes, because I can easily interpret 1 as 1 cubed. And the difference of 2 cubes formula is something that you may have memorized from Algebra 2, and if so, you'll have this. And you can take that, rewrite the denominator, and we could do some massaging to our algebraic expression here before we begin. And now we can write this down here. And you can cancel those out, and you can get this. Now when we do this, our derivative is going to be the same thing, but it'll be just in it'll be an equivalent function, but just with simplified parts. And you might say, well, how can they look, we haven't even done the derivative yet. But when we do, it's going to be much simpler looking than this derivative. I want to tell you ahead of time that if you factored and simplified this, you can factor and simplify and get it to look like the answer we're about to get. I don't want to. I don't have any need for that. I'm just showing you that you could do it this approach, or you can simplify first, and we saw that earlier too. In this case, I do think that this is the ideal approach. Okay, I think it is ideal to simplify first. But there's nothing wrong, and I know that some of you just dove into doing it, weren't sure that you could do that, maybe didn't remember the difference of 2 cubes, and it's perfectly fine. And if you got that big giant answer, this is correct. That's 100% correct. Okay? This is also correct. And when I grade your tests, this is what makes it very hard, is that when I start grading your actual calculus tests, there's going to be more than one way that you can solve these. And there's no right or wrong. There's going to be 2 right ways, 3 right ways, sometimes 4 right ways to do these. Okay, in this case, this makes it a little easier for us. Okay, so now what we're going to do is we're going to do the quotient rule again. But since we simplified things, we have a little less lifting to do. We might even be able to do, instead of writing it out in Leibniz notation, the way I did in the first one, I'll just remind you, I wrote out the whole structure in Leibniz notation. I didn't actually do the derivatives. This one, since it's simpler, I might be able to get away with doing some of the derivatives. So denominator times the derivative of the numerator. Okay, right? Derivative of numerator is fairly routine. 2 times 2 is 4. X to the first. Derivative of 1 is 0. Negative 1 as well. Minus, put parentheses around the entire thing. Okay, minus, so denominator times derivative of numerator, and then numerator times derivative of the denominator. Derivative of the denominator is 2x plus 1. Okay, this one will become 1. Remember, x is x to the first, so we multiply the 1 in front, giving us 1x, and then it's 1 minus 1, giving us 1x to the 0th, giving us 1. And that's where we get that 1 from. And remember, the derivative of 1, what's the rate of change of the slope of the y equals 1 line? Well, it's nothing. It stays horizontal the entire time. And so it's 0, and that one falls out. And all of this over the denominator squared. Okay, now I'm going to multiply some things through. Technically, you're done here. I can't really require you to go past that because that's right. But customarily, we like to simplify a little bit more. So we're going to get 4x cubed plus 4x squared plus 4x. Let's go ahead and expand these. So this is going to give us 4x cubed plus 2x squared minus 2x minus 1. And we're going to subtract each of those, giving us minus 4x cubed minus 2x squared minus negative 2x for plus 2x minus negative 1 for plus 1, and all of that over x squared plus x plus 1. So a little bit prettier, but not too much prettier. So it's kind of pick your poison on these. And h prime of x equals, and now we'll simplify. The 4x cubes dropped out. 4x squared and 2x squared becomes 2x squared. 4x and 2x becomes 6x. And we get 1. And then we drop this down. And you will see when I return to Wolfram Alpha here that that answer that we get from simplifying first is the same thing. There's the answer we get simplifying first, is the same thing as we get when we don't simplify first. And if you ever do something a different way, like if you're using the student solutions manual, which has the odd answers, or you're checking answers in the back and you have something different, this is a great little strategy to do with Wolfram Alpha. Put in the entire first expression that you have, put equals to, and it will know that you're putting a question mark over this and you're testing the equality statement. And if it's true, it will say true, and if it's false, it will say false. So this is telling me here that although the first way I did it was, it was a little bit lengthier, it wasn't too much lengthier than this, was perfectly fine. And in case you didn't snap to the fact that this was a difference of cubes, you're perfectly fine. There's nothing wrong with your answer. And really, in the grand scheme of things, how much harder is it to put stuff in here than it is to put stuff in here? It's kind of 6/2 dozen one the other. The denominator down here is more complex. This one down here is less complex. The numerator up here is less complex. The numerator up here is more complex. So it's really 6/2 dozen one the other, and you're going to be using technology in both of these cases if you were putting in values to figure out slopes or tangents at certain points. So these are equally useful forms. There's really no preference here, and there's no there's no rule in calculus that says you have to simplify. So this is our answer for 46, and our alternative answer for 46 is this one here, and both are correct. So more than one way to skin a cat. Generally speaking, if you can, simplify first. I do think that that's a good strategy. It's not always the case that it's going to make them easier, but generally speaking, simplify first. Okay? But many of you, I guarantee, started off the way that I did it first. So I wanted to show you that embrace that. Don't get lost in the weeds, and then you see them do the difference of cubes in the student solutions manual, or you go to an online resource or something, or you talk to your friend and they're like, oh, you have to do it this way, and then you think that the way you did it was wrong. I just want to emphasize, this is not wrong. This is 100% correct. And as long as you were very tedious and good with your algebra and followed all your steps down, it's not only not wrong, it's 100% correct. And again, when you administer or you're taking these tests on these subjects, there's so many different ways that students will answer the questions. So as a calculus teacher, you have to be prepared for that, and you're never going to mark somebody wrong for doing it a slightly different way. It's just not what we do. And nobody should be doing that at any levels of math, but we know that some teachers do. They're like, you have to do it this way. I don't know why that happens, and none of the teachers that teach higher mathematics, higher secondary, that is, not like topology or whatever, none of the teachers in higher secondary or early tertiary mathematics do that at all, because it's silly. It's just not something we do. It's not required in calculus to simplify. However, it will, generally speaking, make your life easier to simplify first. Okay, so let's go ahead and take a look at 54 now. So everybody write that out. And speaking of simplifying first, the first thing, well, there's two different ways we could do this. It doesn't really simplify pretty, right? We could simplify this into z plus 1 over z, right? Wouldn't it simplify into that? And then that would be z plus z to the negative 1. So that's one way we could do that. I could simplify that into this, and that might help. So we'll go ahead and do a simplify way, and we'll just compare which one's easier. Simplify, yeah, and then non-simplify. We'll do it both ways here. And it looks like a toss-up to me. I mean, that doesn't look really much easier than this. This I do have to do the quotient rule on, and since it's a 2 on the denominator, that means one of those is going to fall out, so I'm kind of inclined to do the simplified way since we have a constant. And the rule I told you is if there's a constant in the numerator or a constant in the denominator, then typically we want to simplify first. So let's go ahead and rewrite f of z like this first. me make sure I simplify that correct. Right, 1, 1, 1, yeah, 1 over z. That's, oh, I don't know why I said 2. See, I'm glad let me double check. Yeah, that's a z. So I was reading my work and I forgot to slash my z, so I briefly said a 2 and said something wrong there, so just ignore that. So z plus z to the negative 1, yep, times e to the z. Okay, so never mind. There is no constant in the denominator, and so a quotient rule would definitely be required there. But again, simplifying it and doing a product rule, a power rule, might be easier. So what we have now is the overarching arithmetic rule we're doing is a product rule. We need to get the derivative, f prime of z, of this function times this function. So derivative of the first one, so first one times derivative of the second one, which is just e to the z, plus second one times derivative of the first one. So 1 plus, and then don't get confused on z to the negative 1. Remember, that's just negative 1 z to the negative 1 minus 1, which is negative 1 z to the negative 2, which is negative 1 over z squared. You'll memorize that eventually, so this would just be negative 1 over z squared. And now we're done, and we have this. And what we can do now is factor, we can go ahead and distribute our e to the z onto all of these. We can pull it out of both. Let me pretty that up and then resume the video. Okay, and so you do all this work and you're like, I'm done, and then you try to check it with the student's solutions manual, or you put the original problem in Wolfram Alpha, or you compare with a friend, and your friend has this, and you're like, wow, yours is totally different than mine. I guess I'm wrong. No, you're not necessarily wrong. You might be wrong, but you're not necessarily wrong. Guess what? This is the official answer in the back of the book. That's the same as this. It's entirely the same as this. Okay? And let's see why. Now, first of all, you can stop here. You don't need to go any further than here. This, again, it increases my work. There's no, like, a certain amount of simplification that's required to be done on a calculus problem. It's just not how it works. So if this is the form that you got because you decided to simplify this into a power rule problem, that's perfectly fine. There's nothing wrong with doing that. And again, we're going to do it in the non-simplified way, but I first want to show you, in the previous problem it was so ugly and big I didn't want to match the answer to the back through simplifying. But we can easily simplify this. This guy right here is going to be z squared plus 1 over z. This guy right here will be z squared minus 1 over z squared. And then all of that will simplify into z cubed plus z squared minus 1 over z cubed. And you get that by just doing common denominators. This one's multiplied by z over z. Here you're multiplying by z squared over z squared. Here you're multiplying by z over z. So just, pause the video, take a moment, think about what I'm doing. Oh yeah, we're just multiplying by common denominators and putting in a different form. And you can see that that's identical to the answer from the so-called back of the book, or if you're using online resources, or if you have access to some other way. Don't panic. Guess what? Your simplified way was just fine. And so you have to trust yourself and trust the math. Follow yourself down the rabbit's hole and just be really excruciatingly careful and tedious and attention to detail with your rules, and you'll be just fine. And I would have stopped here. I would not have gone farther. I would have been like, peace, I'm done. Okay, and because this form right here is very simple and easy to calculate if I have numbers that I need to put in for z. But, if we want to match the back of the book's answer, just to show that we can, this is what we would have got here. All right, so this is our answer for 54. Now, additionally, we want to take this, and we agreed that we would do it in a non-simplified way as well. So I'm going to rewrite it. And we're going to go ahead and solve this without simplifying first. So this is a product rule problem. Product rule is the overarching rule because I have the product of this one. This is my f times my g, if I want to use a dummy variable. Well, we don't want to use f because f's already defined here. So we'll say this is p, some function p, and some function g. And they're being multiplied by each other. So we know that the algorithm of the product rule is first one times the derivative of the second one plus second one times the derivative of the first one. And if we don't simplify, that means we're going to need to do a quotient rule in here. So the derivative of the second one is going to be big. So get ready. So denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. And now we just have to simplify things. So the first thing I notice is that the e to the z and e to the z. That means I can factor out an e to the z and leave all of this gobbledygook inside. So here we have the z squared plus 1 over z. And then I'm going to have all this stuff. But before I bring this one down, I'm going to simplify it a bit up here. So we're going to have 2z squared. That's what that becomes. Then this is just times 1, so we're going to have then minus z squared, and then we're going to have minus 1, all over z squared. So 2z squared, 2z squared minus z squared will just be 1z squared, so we're going to have z squared minus 1. And now we have z squared plus 1, z squared minus 1, and this one's over z squared. So we multiply this guy over by z over z, giving me z cubed when I distribute it, plus z. Everything will be over z squared now. And then I add my plus z squared, my minus 1, and I drop down my e to the z, and put my f prime of z. And you can see that that's the same thing as the so-called official answer in the book. When I finished doing that, I kept these by the commutative property of addition, or associative, commutative rather. I can keep these in any order, but it's equivalent to that. And so you can see that if we do the quotient rule, when we don't simplify this expression first, we get the same darn thing. So again, you can see that my work's going to be cut out for me when I grade your exams, because this is a perfectly fine way to do 54 as well. And you're going to do whatever's comfortable for you. And we might compare. We might say, hey, did you do chain rule there? Or did you simplify first and then do power rule? Or did you do quotient rule? Or did you simplify that and then do the negative power rules? What did you do? And it's good to just check in with each other and see which way they decided to tackle it. And no students ever do them exactly the same, because there's no requirement that you do. And there's no way you could require such a thing. So anyways, let's shift on to 62. We're making good progress here, and let's keep going. And for 62, we can see that we're back to, and I told you this was going to happen. After they teach all these rules, you're going to do this over and over again. And they're going to say, okay, take a derivative, find the tangent line equation at a certain point A, and then confirm both the tangent and the regular function with a plot using either technology or via curve sketching. So let's go ahead and do that. So first up is we need to know the slope at point 1. To know the slope at point 1, we need to know the function machine that gives us the slopes, which is the derivative. So we're going to do that now. So 3x minus 1. So denominator, this is a quotient rule. The rule we're using here is the quotient rule. Denominator times the derivative of the numerator, which is going to be 4x, minus, put your parentheses, don't lose a negative 1, minus the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator. Derivative of 3x is going to be 3. Oh, hey, Amo. We'll answer that question. Does the power rule work for an exponent in the denominator? Or do you have to bring it up to the numerator first and apply the power rule? So we've talked a lot about this in this video, Amo, and it turns out you can do it either way. And you're going to see that covered in this video today. And I will deal more with you separately. And I have my alerts on for Nextcloud. So appreciate that question, Amo. And we've covered that in detail through this video, and we'll cover it more. And the answer is you can do both, if I'm understanding your question correctly. So denominator times derivative of the numerator minus numerator times the derivative of the denominator. And derivative of the denominator is going to be 3. Remember, 3x will be 3x to the first, multiply the 1 in front, so you get 1 times 3, and then it's x to the 1 minus 1, and x to the 0, which is x to the 0th, and that's just 1 times 3 times 1, which is just 3. And the derivative of 1 is just 0. Okay? So I won't keep writing that out. I'm doing that now to just coach you through it. And then all of this over the denominator squared. All right, now we simplify, and we're going to get, whoops, not 4, 12x squared minus 4x minus 6x squared all over 3x minus 1 quantity squared. Now, let's do some more simplifying here. Let's say I needed to, we need to make a tangent line in a plot here. Well, I'm not going to leave 2x squareds, obviously. So we're going to simplify that out, and then I want to see if it even simplifies more. 6x squared minus 4x. I don't think it will, actually. 3x minus 1 quantity squared. Let's see, I could pull an x out, and I could pull a 2 out. When I pull a 2x out, I'd be left with 3x minus, is it just 2? Yeah, it looks similar. I was thinking maybe it would cross out with the 3x minus 1. 2x would be 4x, but it doesn't. So we're good to go. So we have our y prime function machine. We're now going to plug in 1 for a. And so y prime of 1 will be 6 times 1 minus 4 times 1 over 3 minus 1 squared, which is 2 over 2 squared, which is 4, which is 1/2. So now we know our m value. We already knew the x point of our coordinate. They didn't give us the y point. To get the y point, we need to plug 1 into here, giving us 2 times 1, which is 2. So scratch paper. So we get 2 times 1 over 3 minus 1, which is 2, and we get 1. So just double check that again. So 1 squared times 2 is 2, and 3 times 1 is 3, minus 1 is 2 as well, and 2 divided by 2 is 1. So the point is 1, 1. And now that we have our point, our full point, not just the x value, and we have our slope, now we can do our point-slope equation. So this is the tangent line equation. We're going to do y minus 1 equals 1/2 x minus 1. And there's our tangent line equation. And we're good to go. Now, you can leave it just like this. The convention is to put it in, first of all, that is fine. If all I say is to find the tangent line equation, you can stop here. If you want to plot it on decimals or something, typically we want to simplify it to make it a little easier to do that. So I'm going to go ahead and do that now. We get y equals 1/2 x plus 1/2. Now they asked us to plot these with technology. So there's the 2 parts here answers. That's the equation of the tangent line. So that's part A. And then part B we're going to do right now, which is to plot that and the original equation on the same coordinate plane. So we'll start with this. So we're going to have x divided by 2, and then plus 1 divided by 2. And then let's put in our original equation, which is 2x squared divided by the difference of 3 times x and 1. So 2x squared divided by 3x and 1. And lo and behold, you can see right there it is tangent beautifully right there at 1. At 1, 1. 1, 1. Bam. That's 1. That's 1. And that's right where it's tangent, and it looks beautiful. Really nice visual confirmation there, and now 62 is done. So I'm going to stop the video there, and I'll post the derivative video separately. And hopefully that was helpful, and we'll see you all in the next one.